Hello everybody and welcome back to my channel. This is Kshitij, and on this channel we talk about robotics, research and academia. Today we are continuing a discussion in the TT101 Basics of Mobile Robotics lecture series, and now we will be looking into recursive state estimation, also known as SLAM. So here is a brief overview of what we're going to discuss today. So we're going to take a quick recap of what we discussed in the previous lecture. And then we're going to look into what SLAM is and what are the various SLAM approaches. And SLAM stands for Simultaneous Localization and Mapping. So we're going to look into the various approaches that exist in the literature. A high-level overview, but enough depth to get the concept very clear to you. So you have a conceptual understanding. And then in the later series, we're going to look into more details of this and implementation details, etc. And towards the end, we have a very interesting segment for bio-inspired SLAM, which is a up-and-coming segment of the SLAM literature, where we look into inspiration from biology and various approaches that are cropping up from that segment. So first and foremost, as always, we're going to do a quick recap of what we discussed the last time. So previously we looked at mapping and localization separately, various sorts of maps, various localization approaches, and we did a very brief sneak peek into filtering. But filtering is one of state estimation techniques, and we're going to do a bit more detailed deep dive today. And as I said, we're going to be discussing recursive state estimation. Last time we talked about mapping. So here is a one-figure key takeaway from that segment. And in case if you missed the previous lecture, I'll put the link in the I button above. You can check that. And the link to the entire playlist where all these lectures are organized chronologically is also available in the description section below. So if you have your known poses, right? So if you know where you are, by you, I mean the robot, then what you can do is you could map the objects around you with respect to your current location. Right, so this is known as mapping with known poses, and the figure you're seeing in front of you is from a strategic game. And the way you could imagine yourself is, normally there is a character on this map that you could navigate around with your keyboard, and this brightened up area is what you have explored already, and this grayish area is what you are yet to explore. Black area is completely unknown environments, right? So imagine that you're somewhere here at the boundary here, and then you try to navigate here, then this area is going to be brightened up, opening up new avenues of exploration for you. But what this means is you know that you are here, so you know your current position, and you're building a map with respect to the known location, and you're mapping the objects accordingly, right? So this is mapping the positions of the objects with respect to known poses. Now, the inverse problem is localizing yourself. So we take an example of this hiking trail, where typically what they do is they give you some nice landmarks, very easy to locate them, right? So you look at the map, you look at the landmarks around you, then you try and figure out, okay, there's a mountain in front of me, there is a path turning right, there is water to the northeast, etc., and then you eventually localize yourself, say you are here. So this is like manual localization when Google Maps or other technology is not available to you. So what you're doing here essentially is, with respect to a given map, you're estimating your pose. By pose, I mean your position, your orientation, which way you're looking, and you're trying to localize yourself with respect to a given map. Now, in real world, this is often a chicken and egg problem, because to build a map, you need to know where you are, but to know where you are, you need to have a map. And often in real world, the robot is deployed in unknown environments, which means it neither knows where it is, neither does it know what the environment around it looks like. So it has to do both of these things at the same time. Another problem is the problem of trust. So if you've seen my book, I'll link it in the Amazon link in the description below. So you're welcome to buy it and take a look inside it. I go into a lot more detail there. But this is a one-slide overview of the trust problem that I also introduced in my book. So imagine you are an MMA fighter, and MMA stands for mixed martial arts, for those of you that don't know, which means you're going to be capable of multiple martial arts form, and you're fighting with an opponent inside a ring. And imagine that you have an individual coach for each of the martial arts forms. So there's a taekwondo coach, there's a boxing coach, there's a Muay Thai coach, there's a judo coach, thereby making you proficient in, let's say, these four martial arts schemes. Now, the problem is when you are building a strategy while you are in the arena, each of these coaches is giving you some inputs. But who do you trust? And all of them speaking up together is going to create a lot of noise. Then, but as a fighter, you have very limited time to take a decision and then act upon it. Analogous to this, imagine this is your robot deployed in an unknown environment. This arena is the environment. These coaches now are your sensors. So the robot doesn't know which sensor is noisy, and if so, how noisy. So it doesn't know who it can trust. But all of these sensors are reporting some information to it, and it needs to kind of make some heads and tails out of that information. Now, this is essentially what we do under simultaneous localization and mapping, where you try to fuse the information around you to build a map and localize yourself. So as I said, the problem always is that the robot doesn't have a predefined map in an realistic scenario. So it would be deployed in an unknown environment. So you have to build a map and localize simultaneously and recursively, because remember in the previous lectures, we referred to this thing that the robot moves, which means the sensor data changes, the environment changes. So it needs to do this repeatedly every time things change. And hence the name Simultaneous Localization and Mapping, or SLAM for short. So you're recursively estimating your state. Now, there are a few different approaches for solving the SLAM problem, as we say it. So as I said, SLAM is a chicken and egg problem that needs to be solved, right? So it's not an unsolved problem, so to speak. It's, at least for the last 3 or 4 decades, a lot of significant research has gone into SLAM approaches. And this lecture is going to give you a brief summary of what those approaches are. So we categorize them into filtered-based approaches, keyframe-based approaches, bio-inspired approaches, and a few others. So filter-based approaches are, you recursively do the state estimation while maintaining a robot state as a probability. And then there are some examples like Kalman filters, particle filters, and we're going to look into those in just a moment. So they filter, remember in the previous lecture, I gave you an example of the misnomer, right? So filter doesn't mean throwing away the data. Filter means fusing away what's the most sensible thing and then coming up with an estimate of the most likely state that the robot is in at the current time, right? So even if filter sounds like coffee filter meant to throw away stuff, this is more like aggregator, which is fusing information from all over the sensors. So it's like the fruit infuser bottle that I showed you in the previous lectures. Then there are keyframe-based approaches where we're going to look into what a keyframe is, and then what they essentially do is they just, for the sake of argument, they're just going to save some keyframes from what the scenario is around the robot, and then they're going to build an estimate based on the keyframes. And then there are some approaches that are very well known in this segment. Another segment, which is graph-based. So as the name suggests, there's going to be an underlying graph structure that the robot is going to build based on the measurement that it gets and the estimates that is making for the states and how it moves around. And there would be nodes and edges in a graph, and your objective is to optimize the graph, the structure of the graph. And last but not the least, the bio-inspired methods, as I said. So we're going to quickly take a look at what those are. Okay, so this was the quick sneak peek we saw in the previous lecture, but we didn't go into the detail, but today's the time we do that. So filters, we could split them into two chains. We're going to only look into this chain for the scope of this lecture. So Bayesian methods, there could be Gaussian filters, there could be, which most prominent ones are Kalman filters. So you could have unscented and extended Kalman filters as an extension to this. There could be Gaussian mixture filters, which we are not going to discuss. Then there could also be particle filters, which is non-parametric filters, so they are non-Gaussian filters. And then there is a hybrid filter, Rao-Blackwellized particle filter. So we're going to look into Kalman, extended, unscented, particle, Rao-Blackwellized in the scope of the Bayes filter, and then we're going to move into other approaches that we discussed beyond filter-based SLAM. Okay, so first things first, Bayes filter. So one thing you should carefully understand here is that Bayes filter is essentially, again, a misnomer. Bayes filter itself is not a filter, it's a probabilistic framework. Then there are filters that build on top of this methodology, which are capable of filtering the sensor information and fusing it for you. So in this framework, what we do is we do recursive state estimation to update your current belief based on most recent observations and what control commands you gave to the robot. Say you said to the robot, move 5 meters straight, or move, turn right 10 degrees, etc. So whatever your control command was, whatever the robot is observing after execution of the commands, it uses those information to update the state about what it thinks is what it believes is the state of the robot. Now, some realizations of the filters include Kalman filter, extended, unscented Kalman filters, particle filters, and we're going to look into those next. So let's start off with a discussion of Kalman filter, what it is and how it works, right? So a robot is essentially a dynamic system where the state of the system is going to keep on evolving. Now, state of the system, as we saw in the previous lecture, could include multiple different things, but for the sake of this argument, we're going to say I'm interested in estimating the position of the robot, or position and orientation, meaning I want to know the pose of the robot. And for simplicity, I'm only interested in 2D pose, so X, Y, and yaw of the robot. Now, the problem often in real world is that what you want to measure is the true pose, but what you can measure are indirect observations. You only have access to things like IMU data, odometry information, maybe some sonar readings, which are indirect observations, and you have to use those to make a state estimate for what the true pose is supposed to be, which you cannot directly measure, right? So as I said, these eyes represent what you can observe, and then you're giving some control commands to the robot, so you also know those, but you don't know what the true pose is. So the best you can do is you could estimate the pose, and you could recursively update the estimate based on what you gave the control command, what you're observing. Oh, and the observations also include the sensor data, of course, which is not shown here. And you do this in a cycle. One more thing that you have access to is expert knowledge. See, you as an external observer know something about the environment that the robot is going to be operating in. Oftentimes we call it unknown environments, but there is, from past experience, you might know something that might help, robots as well. So let's call this expert knowledge, or some sort of prior model, or whatever you want to call it here. And okay, this top part is the same what we saw in the previous slide, right? So you want to estimate the true pose, but you don't know what it is. You can't measure it. You have to estimate it somehow. So we take a copy of the control commands, feed it to whatever this prior model that you can make based on the expert knowledge, and you try to estimate what are the observed variables going to be. So this approximate sign represents an estimation, and your mission now is to make these estimates as close to the observed values as possible, hence this equal to operator. And the way you can understand this thing is, the more close this estimated value and observed value is going to be, the more close this estimate pose and true pose is going to be. Okay, here at least you have the ground truth, so you can evaluate how good were you doing with your predictions. But here you don't even have the ground truth, so you just have to, whatever is happening here, the same performance is going to be here, is what we're going with. So for the electronics people, you're going to like it this way. So oftentimes we also represent this as a sort of circuitry diagram like this, equivalent to a schematic. So the idea is to minimize the error between what you observe and what you estimate, such that the estimated pose tends to the true pose. And you could draw it like that, where y being an observation and y hat being an estimate. You calculate the error and you feed it back to your system model based on your expert knowledge. And you add a Kalman gain, which is a multiplier to the error, which basically dictates how quickly does this error need to converge for this pose to converge to the true pose. And this essentially is the working principle of the Kalman filter. And you do this recursively, because every time you make a prediction, you get new data, you rectify the error, then you update your predictor, and then you rinse and repeat until you have converged. So As in the previous lectures, here's your first pop quiz. Can you think of some real-world use cases of Kalman filter? Where would such a filter or recursive state estimator be useful to us? And to answer this question, you can use the comment section below where you first mention the pop quiz number and then you could place your answer. Alternatively, you could also join our Discord community for an active engagement with the rest of the community, the link to which will be in the description section and also in the channel bio. So let's try to introduce some math in here and look at some of the assumptions that a Kalman filter makes. So the nomenclature is as follows. The state of the robot is given by an X, the observations are given by Y, the current time step is given by T, the control commands are given by U, and noise is given by W of T, the current noise, and V of T, also another form of noise, because we're going to have two models here. So normally you have two sorts of models, both noisy. So first is called a state transition model because from the current state you move to the next state. So there is going to be some sort of transition that is happening between the states, and this model explains that transition. Essentially what this is saying is your current state is a function of your previous state. Sorry, this is a typo here. It means the previous state and what control commands you gave to the robot, and then there is noise. Okay, so you have this X, some constant A, some constant B, and a noise model here. This is Gaussian and this is linear. Okay, you don't see any second order, third order polynomials here. This is a linear function. Similarly, the way you observe things is given by your current observation is a function of your current state and some noisy observations because sensors are often noisy. So the assumptions here are that all models are linear. By all models, I mean the state transition model is a linear function and an observation model is also a linear function. And they are both Gaussian in nature. Now, why is this assumption a problem? Because in real world, oftentimes the system dynamics are nonlinear. So we're going to make some adjustments here. So here I fixed it, so it's a past state. So what we're going to do is instead of this linear transition model, we're going to make it as a function f of the previous state and the control commands and the function g of the current state, where f and g are now going to be nonlinear functions. And this is an additive Gaussian noise, which may or may not be additive. Sometimes it would be multiplicative or some other nonlinear combination, but you have to carefully adopt for this. But for the sake of this argument and moving further, we're going to introduce what is known as an extended Kalman filter, which is going to deal with this nonlinear system dynamics for both our state transition models and observation models. So let's carry over these equations to the next slide. So the F and G are still here, and we're going to introduce the working principle of the extended Kalman filter. Now, what this does is it's going to use the same trick as a Kalman filter does. So if these were linear equations, we know how to deal with them. So what this is going to do is it's going to do what we call as a local linearization based on Taylor approximation. So it's going to expand upon this equation, and instead of directly dealing with this nonlinear function f and g, it's going to introduce rate of change. So you're going to introduce a rate of change of x and rate of change of y is given by this equation, which is linear about the mean of the current state estimate x hat of t, where capital F and capital G are Jacobians, or also the slope of the function or the rate of change of the variable at the point of consideration, which is the mean of the current state. So this is now doing local linearization about the mean of the current state every time, even if you're dealing with nonlinear state dynamics. This is now an extended Kalman filter. So the question for you is, although I explained that the Kalman filter has an assumption that it's dealing with linear system dynamics, what happens if you try to apply a Kalman filter to a nonlinear system, which has nonlinear dynamics? I mean, you just imagine you simply ignore my advice and you still try to apply a Kalman filter to a nonlinear system. What's going to happen? And another thing for you to consider is, what challenges could you expect now that you know that we're going to use Jacobians for an extended Kalman filter? To give you a hint, focus on the word Jacobians. This is going to be a bottleneck of some sort. So whatever is going to be the problem with the Jacobians is going to be the problem with EKFs. Your quest is to figure out what challenges is the Jacobian going to pose. Moving further, because I already gave you a subtle hint that the Jacobian is going to give you some trouble, we're going to introduce what is known as an unscented Kalman filter, which is an even further extension of the previous variants that we saw. Now, what we saw is a Gaussian distribution, and it is going to go in non-linear transformation, which is given by this function f, which we saw in the previous slide. Now, what we're going to introduce now is this thing called sigma points, which are these colorful points that I have shown here. They're belonging to a set of some math cal x. And each sigma point is basically the distribution of the sigma points is going to have the same mean and safe covariance as the underlying probability distribution, but they are going to go the same unscented transform as the function is going to go through this nonlinear transform. And now we're going to only deal with sigma points, which are, like you could imagine, representative sample points of the function post the transformation. And we're going to compute the new mean and covariance of this function given by the sigma points, but these are not arbitrary points anymore. These are now weighted sigma points. Okay. And then you use this transform distribution to compute the new state estimates. So because it goes what is known as an unscented transform, this is known as an unscented Kalman filter. So these points, they go a nonlinear transformation here, and now they're given some weights. That's why the distribution is no longer similar to this. Now the question for you is, can you point out the fundamental distinction between the working principles of EKF and UKF? And to help you with this, you could think in terms of the sample points we're going to use to model the original Gaussian distribution. So for UKF, I introduced sigma points. What I left blank for you is to figure out what we use for EKF, and then how does that affect the working principle of the two. Okay, so this is something to get your brain going and trying and comparing the two methods. So before we look into the non-Gaussian extension, which is the particle filter, here is a contrastive summary of the methods we have looked at so far and why we're going to look at the particle filter next. So we started off with the Bayesian filters, which are these three, and they are extensions. So Kalman filter is for a linear Gaussian model. Then we figured out that often the real world is non-linear, so then we extended it to locally linear approximation of Gaussian model of nonlinear dynamics with a Gaussian distribution underneath. Then we extended it to unscented Kalman filter, where we're no longer doing local approximation, but it's directly doing the unscented transform, allowing you to deal with highly nonlinear dynamics. And Kalman filter, if you think about it, is the best linear unbiased state estimator with low computation cost, meaning if the state dynamics can be linear and Gaussian, then there is no way you can perform better estimate than a Kalman filter. Extended Kalman filter has low to medium computational complexity depending on how much pain does the Jacobian give you. So I've already hinted that this is going to be the bottleneck somehow. You have to figure out what that bottleneck looks like. And the unscented Kalman filter is going to be medium computational cost. Sorry, this needs to be UKF, not EKF. And then we're going to start talking about particle filter. So particle filters are nonlinear, non-Gaussian models. So they are completely non-parametric now, and they have a high computational cost, which we're going to look at in just a moment. So basically, we went from linear Gaussian to locally linear Gaussian to fully non-linear, but now we're even extending one step further to non-linear, non-Gaussian. That does come at a cost. We're going to see soon. So the working principle of a particle filter is as follows. So imagine you are given a map. So I'm simplifying the problem. Instead of doing the full slam, we are now going to do state estimation in terms of localizing the robot first. So these ellipses are now particles. And what a particle represents is a hypothesis about the current state. Think similar to a sigma point we discussed in UKF. And you can see that I have deliberately drawn these particles that are, some are slightly smaller, some are slightly bigger, some are oriented differently. So what it is representing is the confidence on the hypothesis that you are here, or maybe here, or maybe here. So the smaller the particle, the lesser the confidence. The bigger the particle, the higher the confidence that this hypothesis about your current pose, current state is very likely. So the way the particle filter works is that you sprinkle out multiple particles around the environment, and then as the robot moves, you gather evidence, which is sensor feedback, and then you try and evaluate the hypotheses by giving them some weights. That's why their sizes are a bit different. And then you update the likelihood of being in that state, that hypothesis, based on the observations. And over time, as you do this repeatedly, the unlikely particles are going to diminish. There are a few other additional steps such as resampling, etc., but we're not going to go into the details. But the high level aspect of that is that, sometimes because the particles diminish, you might end up losing an actually likely particle, a likely hypothesis, by mistake, because they die over time. So resampling is basically, respawning particles in the area where they still stand a chance, so that they get another fighting chance. But not going into too many details at the moment, you just have to understand that, okay, over time, these particles are going to diminish, and then you're going to end up converging your particle cluster to your most likely current state estimate. Now, one caveat here is that you need a lot more particles to have a significant coverage as the size of your environment and the complexity of your state grows. Imagine instead of just doing a 2D state estimate, you're doing a 6-dimensional state estimate, or your environment is highly complex, very large, you need a lot of particles to cover all the area, then you're going to need a lot of computational power. That's just one big problem that we have to deal with here, even though the idea is very nice because it doesn't have any assumptions in terms of the Gaussian nature or linearity, etc., that we saw were the limitations prior to this. So nonetheless, can you think of some real world use cases of particle filters? And building on top of this, another related question is, when do you use Kalman filter versus particle filter? Can you think of some scenarios where Kalman filter makes more sense versus a particle filter? Okay, while I leave you with that cliffhanger, we move to the Rao-Blackwellized particle filter, which I explained in the flow chart as a hybrid filter, and we're going to look at it just now. So remember that the scope of this lecture is SLAM, meaning we want to do both simultaneous localization and mapping. So far, we only looked at the use of particles for localizing the robot, but what about if you also need to build a map? I already told you that the computational complexity is just going to explode just by trying to localize yourself. Imagine adding another complexity where you have to build a map on top of it. So for this, we use a trick called Rao-Blackwellization, which is a factorization technique that exploits the dependency of the poses on the map and vice versa. Simply speaking, the intuition behind this is that if you assume that you're given a trajectory, that a robot followed a certain path, then what is the map given this trajectory? It's highly dependent on what the trajectory is. You're only going to see certain segments, certain orientation, certain appearance of the world if you follow that trajectory. If the trajectory was a bit different, you're going to see a different aspect of the world, right? So this is essentially what we're going to harness, and vice versa, right? So if you're given a map, there's only a particular path you would have taken to have the world look the way it does. So this builds on conditional probability distribution. So the joint probability is given by this conditional probability and then the P of A. So what Rao-Blackwellization does is that it says, if this conditional probability can be computed efficiently, you can use samples to represent this and then obtain this for each of the samples. Now, how does this apply to the SLAM problem that we're talking about, filter-based SLAM? So we're going to say A represents the trajectory and B represents the map. So SLAM essentially is building a joint probability distribution. For filter-based SLAM, we are building a joint probability distribution over the trajectory that the robot took, so the poses, and then the map that That's why you're doing mapping and localization, and that is given by the conditional probability that the world looks a way that it does given the trajectory, and then probability of the trajectory being the one that you've selected. So we're going to start off with this, where we are going to use particles to sample the trajectory first, and then we're going to build a conditional probability for every sample. So again, the way this works is, say you have a particle I with whatever is the weight for that particle, that represents the full trajectory that the robot took. So if you say whatever this particle is saying is correct, and that is the trajectory that the robot took, if true, what would the world look like? Say the world looks like this, and that's the map that you have. Then there's another particle J with whatever confidence you have on it, that which represents another trajectory estimate. If that were true, what would the map look like? And that's another map you have. So these are various hypotheses of the maps for each corresponding sample trajectory. And then you try to use the sensor data to gain evidence and then adjust the weight and the confidence of these particles. And then you end up with your most likely trajectory and the map. That's why it's a bit hybrid modeling. So this Rao-Blackwellization helps us use particle filters for both mapping and localization. Okay, so that was the end of the filter-based SLAM segment. Now we're going to move into another segment called the graph-based SLAM. Now, in the graph-based SLAM, we're going to look into the nomenclature, which is going to be slightly different from what we saw before. So the poses of the robot are now called nodes. Let's say these are in R3, which means you can have XY position and yaw angle. So we're talking about a very simple robot plane, operating on a ground plane. Could be high dimensions as well. Then instead of having, graph typically has nodes and edges, where edges are the connectors between the nodes that represent the connectivity of the graph. Here, instead of having straight line solid edges, we can imagine that they are some sort of springs, and you're soon going to see why we're talking about springs. Some people also refer to them as rubber bands or elastic bands, is the same notion. Then this muscle symbol that I put here is the elasticity or the spring coefficient, like how strong or how soft the spring is and how much is the tension in there. So essentially what we do in a graph-based SLAM is we try to capture the following constraints. What is the initial location of the robot? Relative motion constraints, kinematic constraints, because there are some motions that the robot can and cannot do. These are kinematic constraints. And then the relative measurements that the robot is going to see based on the nodes and how it went across the graph. And these constraints are captured between the positioning of the nodes and these springs and the strengths between them. Right, so imagine that the robot went this route, then you're going to get these many nodes and then the connectors between them. Now, the reason why we talk about these connectors in terms of springs or elastic bands is because of the very important concept called the loop closure. Now, loop closure simply means that you are revisiting one of the locations that you've previously visited, and there is certain drift in your understanding of where you are, so you're trying to correct for it. Now, why would anyone want to revisit? So see, in SLAM, this is very important to revisit the areas where you're damn sure that you know where you are. This is why it works. So imagine you are exploring an environment and you're given certain landmarks or certain areas where you're damn sure that you know where you are. Okay. Then you start venturing out even more, and then you suddenly get lost. Lost in the sense, maybe you have a broken sensor, maybe you have some problem with your calculations, or for whatever reason, you suddenly lose track of where you are. You can always backtrack to the previously known location and then start out again. That's why you want to keep revisiting your last known locations to make sure that you're not getting lost or you're not getting overconfident with where you are, but you're actually somewhere completely off, right? So this is basically to recalibrate and realign your estimates with the ground truth. And this is why having the spring-like network for a graph is very useful, because say your robot went this route, then it took another step, and then it took another step. Now, in the robot's mind, it thinks it is here, but in real world, the sensor observation of the landmark that it sees from here and that it sees from here is exactly the same. Now, for a fact, you cannot be in two different places and have the same observation, right? So the robot knows, okay, there is a drift in where it thinks it is versus where it actually is, which means this location should actually be here. Now, this is where the Spring network is going to come in handy. What it does is it's going to add another string here with a nominal length of 0, which means these two things need to converge and come on top of each other. And whatever is the strength that you inject here, the other springs need to accommodate for the strength. And so they're gonna move around, adjust so that the net everything comes to an equilibrium. So you could imagine if you have that bunch of balls connected to each other with a spring or a rubber band. If you move one ball, the others move to realign and readjust so that the system stays at equilibrium at all times. And the same concept applies here. So that's why these spring-like adjustments are very useful. So this is the underlying principle of a graph-based SLAM. Now, assuming that the robot is able to create a pose graph because each of the nodes represents a pose, and then the underlying feature that you get is a graph. Using a sensor of choice, could be sonar, laser, lidar, etc. It is able to localize itself. Now, what kind of maps can you build with it? So remember in the previous lectures, we talked about a few different kinds of maps. So the brain teaser for you here is to figure out, if you're given a pose graph, what kind of maps can you build on top of that? And then, we talked about, so this next pop quiz relates to this aspect of loop closure. So remember that I said that the robot can never fully know whether or not a sensor is faulty, right? So say that there were some sort of wheel slippage or a broken sensor or whatever XYZ issues that made the robot think that it is actually here, even though if it wasn't. Maybe it was just hallucinating. I don't know. There's some sort of problem. So it falsely detected that it needs to do a loop closure. So it's a false positive, and it actually went ahead and did it, right? So what would be the effects of doing a faulty or a false positive loop closure on the overall graph? And I'm sure by now your brain has already started figuring out that it has to be an adverse effect, because otherwise I wouldn't be asking this question. So to further expand on that, can the graph ever be recovered and rectified if a robot were to go ahead and do this faulty relaxation or faulty adjustment? So this is something for you to figure out, whether that's gone forever or whether there is still hope. And also, you should check out this video by Brian Douglas from the MATLAB Tech Talks. This is the link to this video, and you could also look it up. Brian Douglas, MATLAB Tech Talks, graph-based SLAM. He has a really nice animation that shows you the effect of the spring as the robot moves around. So what he's doing here is there is a real robot with a laser scanner in a simple environment with one object inside. And he's trying to build a map and a pose graph. So what he's doing very nicely here is, this is an estimated robot pose, this is a real robot pose, and as the robot moves around, there's going to be drift. And the sensor data is no longer going to be aligned with the real data. So then the springs are going to come in handy and try to pull things and push things and try and realign the data so that the map is somewhat coherent. And this video is going to give you a really nice intuitive understanding of how this graph relaxation and realignment comes into picture. So do give this a watch. It's a very nice animation. That's why I didn't do it myself, but this is very self-explanatory and a very nice video. Okay, so moving on to the third segment of the SLAM, which is a keyframe-based SLAM. So keyframe, as the name suggests, is something very important. What's important here is that it's a most representative poses that you could use to localize yourself and build a map. Instead of keeping the entire history of poses, now you're only selecting some representative poses. So if you're familiar with graph networks and graph theory, essentially what you're doing is, you're trying to prune the graph such that you're only having the bare minimum number of nodes and edges in the graph as required for doing the SLAM problem, right? Instead of having the full history of the entire poses and the entire edges that connect to them. So this is kind of like reducing the amount of computation and the efforts that you need to do to optimize the graph. And then what you do is you retain a window of the most recent keyframes, and then you try and optimize the graph based on those. And you, of course, also retain the dependencies between the keyframes only, and you forget about the rest of the edges in the nodes. So this is the working principle. So say you get a new keyframe, you do the feature extraction within the keyframe, and we talked about various sorts of features and what they are in the previous lectures. Then you track the features between the frames. So some of the features, maybe you found some key features in the previous frame and they might have just moved around, or they might have disappeared and you might have gotten new features. So there is extraction and tracking going on. And then you use this information to figure out how the robot or the camera or whatever sensor has moved. So you're estimating the motion of the sensor / robot. And that's how you're able to localize yourself. By decoding how the features moved, you try to decode and map them to how the robot or the sensor moved, and then you've localized yourself. And you use this information to select a new keyframe and detect if a low closure needs to be done, and then update and relax and realign the graph and manage the springs. And then you're basically doing the mapping step. And then you ask yourself, is there a new keyframe or are we good? Because remember, I said there is a window of the keyframes that you want to keep, and you want to keep this to the bare minimum. So you don't want to randomly keep adding new keyframes every time a frame comes into picture, but you want to only retain the most representative poses, right? So the important decision-making criteria is there a new keyframe here or not? And of course, we're not going to go into details of how and when you detect there's a new keyframe. That's for a later advanced level of this lecture, but you should keep this in mind, that this is essentially what you're trying to figure out here. And then of course, you have to select what features are the most sensible for your application of interest. Okay, so we looked at filtering-based SLAM, and then we talked about keyframe-based SLAM. So in terms of memory and computational complexity, you should try and contrast them and figure out which one looks to be, at least on paper, more memory efficient and computationally efficient. And as I said, there is going to be a window of the keyframes that you use to optimize the underlying graph structure. So do you see any problems with the windows-based approach? And one of the most prominent examples of keyframe-based SLAM is what is known as the ORB SLAM, which is a highly scalable and robust visual SLAM. So they are built for cameras that are monocular and RGBD cameras. And as I said, you have to do it's all about the features that you use from the keyframes to estimate the poses. And this is a visual SLAM approach. So they use what is known as the ORB features. Now, ORB features are something very special. ORB features are oriented fast and rotated brief features, and in short, they are known as ORB. And the key term is that they are using oriented versions of the fast features and rotated version of the brief features. So it kind of builds on top of the two already known and well-prevalent features from the visual community. So fast features are features from accelerated and segmented test. What they do is they compare the intensity of a given pixel within its neighborhood. And typically this is like 16 neighbors around that pixel of interest, or your query pixel. And what ORB does is now there are no orientation factors involved in this. So it tries to incorporate orientation as well. And then there is these brief features, which are binary, robust, independent, elementary features. So as the name suggests, these are elementary features, right? So what they do is they take the key points that are found by the fast features, and they try to make a binary feature vector to represent the object, what is being represented by those keyframes. And then ORB, instead, these are not rotation invariant. So ORB uses what is known as the rotated briefs. And it puts these two things together to try and evaluate your keyframes, find what are the features, track them, and extract them. This is a very awesome algorithm in the computer vision community and the visual SLAM communities. I think it has about 3 variants launched by now. They are very highly cited and very robust, computationally very efficient. So feel free to dig through them and read their research papers and look up their slides, etc., if you're interested in learning more about what ORB SLAM does. Another prominent keyframe-based SLAM approach is what is known as the cartographer SLAM, which was introduced by Google. And this is also a very interesting concept. So remember that the graph needs to be adjusted and aligned, and the springs need to be adapted based on doing the loop closure. So this is essentially doing that very computationally efficient manner. And how it does this is it takes the sensor data from the onboard sensors, and imagine you're working in an unknown environment. And as the robot is exploring the environment, it tries to build submaps instead of keeping one global map. So it does this in a lower level, and then there is a higher level. So it's a hierarchical framework. Or you could talk about this as the higher level, and then there is a lower level, whatever. It's a matter of perspective. But on one level, it is going to make submaps, which are just like parts of the full map, and they need not be the exact same size. The dimension of the submap is determined differently. Let's not get into that. But let's just say you're building like chunks of the entire map at one level, which is known as the local slam. So you're building the trajectory that the robot is taking. And then eventually what you're going to do is you're going to do global slam, where you're going to stitch everything together. And when you're building sub-segments, some of these might be misaligned based on whatever local information you had in that submap. So essentially the job of this cartographer would then be to resolve these kind of misalignments and align them properly and build a globally consistent map and do the loop closures as and when detected to give you the final slam, right? So this is a very computationally efficient solution, primarily used with laser scan data for indoor environments, but it's a nice to know algorithm for keyframe-based SLAM. Now we're moving towards the last segment of SLAM, which is the bio-inspired SLAM. So starting off, we're going to talk about this very interesting SLAM approach that came out of Australia from Professor Michael Milford at QUT, and this is known as RAD SLAM. So in the neuroscience literature, a lot is known and understood about the rat brain when compared to, let's say, human brain, because ethics considerations, you can't stick any electrodes into a human brain, and people tend to not know what they're doing. Like, you can't ask a human to explain what's going on in their head. Sometimes they don't even know, sometimes it's just misleading information and a whole bunch of other things. So what this does is the rat slam relies on the extensive knowledge from the rat literature and rat hippocampus, part of the brain, which is known to be contributing to navigation and slam and planning. And they build an artificial model of that to deploy on a robot. Actually, they just built an artificial neural network and deployed it on a web camera mounted on a car, but it has equally been deployed on robots afterwards. So what this does is, inside the rat hippocampus shown here, there are two kinds of cells that are primarily of interest to us, although there's another cell and there are a few other cells like the boundary cell, etc. But place cell is the neuron that fires when the rat is at a particular place in an environment, hence the name. And head direction cell fires in a particular orientation. So when the nose is pointing in a certain direction, then the certain head direction cell is going to fire. So position and orientation are decoded in two different cells, and together they would represent the pose of the robot or the rat, etc. So essentially the idea here is to build a neural network that mimics the firing of these neurons so that you're able to localize yourself. And that is done with what is known as a convolutional neural network, which we're not going to get into details with, but you could easily look up this paper that was published on OpenRATSLAM. This is an open source code. So if you want to play around with it, you could play with it. It even has data sets. So this is the rat robot. This is an arena they made indoor with an overhead camera to give you a top-down view. And this is the pose graph that this algorithm is making with the underlying neural network and the firing of the neurons, etc. And they're also using graph relaxation here. So eventually, when all the relaxation happens, the graph, this is actually a graph, but the cool thing here is that the graph actually starts to resemble the real environment. So you could do a direct comparison whether or not your map or the pose graph is making any sense. Otherwise, if you have an abstract graph, then you have to come up with metrics to figure out if that graph makes any sense or not. Here, there is a direct visual comparison. So this was a very interesting concept. And what they did in RATSLAM was for 3D pose estimates, because RAT is doing so X, Y, and Yo, and they used the camera feed as a visual input for building the map. And as I said, so from Professor Michael Milford, I think in the early 2000s. And then since then, a lot of work has been done so far on it, and even other bio-inspired approaches like fish slam and whatever animal slam have come out after that. But what we're interested in is that in my previous collaborations, we also looked into what is known as the Whisker rat slam, which builds on top of this, still uses 6D pose estimates, but instead of visual input, we start looking into tactile input, hence the word whisker. So what my collaborators did, you could look up this paper if you want to, on whisker rat slam, but essentially what they did is they made this biomimetic version of rat whiskers. I also talked about a version in my previous lectures. And they started using that sensor information to estimate the pose of a robot, where the robot here was a UR5, so a manipulator. And that's why you needed 6 degrees of freedom. And that's why you had to increase the complexity of what the rat slam was capable of doing to incorporate for 6 degrees of freedom. And that was an interesting concept that came out there. And then I, with this previous student that I co-supervised, we went in and what we did is we came up with a way to fuse visual information with tactile information to do 3D pose, which builds on the underlying framework of RATSLAM. And that was called VitaSlam, Visual Tactile Slam. Not going into too many details at the moment, but this is a published work. You can look up the paper, or you can even write to me if you want to know anything about this idea. So this was like a brief overview of what we did so far in the animal kingdom, but I also went ahead and looked into humans. So I connected with a cognitive psychologist in Australia and a neuroscientist also in Australia, and we were discussing like, okay, what can we learn from a human brain when it comes to navigation? Turns out virtual reality was an interesting tool where we could use the goal-directed navigation principle and then, reverse track from there what happened in a human brain. So what we did was we made a sort of game inside virtual reality with non-repeating textures. And we put a countdown timer to put some pressure on the person to try and complete the mission. And the mission was they started off from somewhere, let's say this part of the arena, and they had to navigate to a goal. Now, instead of giving a pinpoint location, what we did was we used the firefly sort of buzzing, let's say noisy visual cue that was spinning around in some region around the actual goal. And what their mission was to navigate to this region and try and get to the actual hidden physical goal, which is determined by the score. The higher the score, the closer you got and the faster you got there to the actual physical goal. So they had to decode where could this goal be. And they kept on repeating this in a few trials and then optimizing their trajectory and their mission strategy. And eventually, once you have this trajectory data, you could build machine learning models out of that. And that basically is your decision-making framework or the navigation framework as a replica of the human brain. So this again is a published work, it's open source, so feel free to play around with this environment if you like. And the idea was to understand, human-inspired SLAM, if you want to do it without sticking in electrodes, what would that look like? And this also has the capability of using light and sound as an additional sensory modality. So if I turn off the lights and you're navigating in a dark room, if I turn on the sound, so the buzzing of the fly is the only thing guiding you, or vice versa, or a combination. So you could play around with, sensor fusion and its effect on navigation and their ability to find the path and so on. So this is also a first step towards building a human-inspired SLAM. Okay, so that was it for today's lecture. And I hope you got a decent understanding of what recursive state estimation is and how we do SLAM and the various categories of work that have been done in SLAM so far. Feel free to like, share, and comment on this video and let me know what you liked about this video and if there's anything else you'd like more clarifications or details on. Share this video with the other learners and subscribe to my channel and hit the bell notification so that you're notified as soon as the next lecture goes live. And with that, I'll see you next time.